solutions, and solubility. Are you ready? All right, so do you remember this classification of matter? We have matter, which is composed of mass and volume, and it can either be a pure substance or a mixture. And then within pure substances, we have two categories. It can either be an element with only one kind of atom or a compound with more than one kind of atom. And then on the other side, we have mixture. And what is a mixture? Well, it's composed of two or more pure substances. And then if the particles are evenly distributed, we have a homogeneous mixture, uniform. And if they are not evenly distributed, we have heterogeneous. You should remember that. All right, so what's a solution? Well, a solution is a type of homogeneous mixture. It's symbolized with AQ if water is the solvent. What's a solvent? Well, let's see. It's one of the parts of a solution. So a solution has two parts. We have the solute, you put it in, and the solvent does the dissolving. Okay, so the solute, you put it in, the solvent does the dissolving. Okay, if you see AQ after something, it means that it was dissolved in water to make the solution. Solute, the substance you put in, it's being dissolved. Solvent is doing the dissolving. And altogether, the solute with the solvent make the solution. Solutes can be solids, they can be liquids, they can be gases. So you could take Kool-Aid powder or a dye tablet like this if you ever dyed eggs, and you can dissolve it in water, a liquid. You could also dissolve it in alcohol, which we sometimes did to change what the dyes looked like. You could do a liquid solute in a liquid solvent. You can also do a gas solute in a liquid solvent. So you can see that we're focusing on liquid solvents. In reality, there are other kinds of solvents, like you could melt things together and make a different metal that is technically a solution. You can have a solution that are gases, but we in this course focus on liquid solvents. So what you should know is that liquid solvents can have solid solutes, liquid solutes, and gas solutes. Now, not every solution is the same. In class, we're going to do a short little activity. We're going to use a cup, put some water in it, add a sugar cube. And we're going to look in the cup. Is the sugar dissolving? We're going to talk about it. And then thinking about how could we speed up that rate of dissolving. We just plopped a sugar cube in the water. How are we going to speed up the rate of dissolving? Do you have any ideas? Well, one way is to stir, agitate it, mix it up, shake it in some way. And that increases the rate of dissolving. It happens faster. I mean, can you imagine if you were making Kool-Aid and you just poured everything in, then just put that in the fridge and just hoped it all figured itself out? That'd be weird. We could also increase the temperature. So if we use warm water or hot water, it's going to dissolve a lot faster. Do you remember when we did the Alka-Seltzer? Do you remember the time for how quickly it dissolved when we used hot? All right, so technically, if you wanted to make Kool-Aid and wanted it to dissolve the fastest, you would use hot water. Just not if you wanted to drink it right away. We could also increase the surface area, so use little pieces. So powders are going to dissolve much faster than big tablets. Again, not every solution is the same. So how could we change the concentration of a solution? Like in our example, we have sugar and water. How could we change that concentration? Think about it. Do you have any ideas? Well, we could change the amount of solute. What do I mean? Add more, add less. So if we add more, it's more concentrated. If we add less, it's less concentrated. We can see that visually, like if we had 1 drop of food coloring, very pale. Add 2 drops, gets darker, more gets darker, okay? More concentrated. There's more of the solute present, okay, in a specific amount. So you see in this picture right here, we have the same amount of solvent, right? So that is kept the same. So then the concentration changes based on the amount of the solute I add. But I could also change the solvent. If I add more, like if I make some Kool-Aid, I'm like, man, this is too sweet. I could add some water, dilute it, make it less concentrated. Okay. If I want to make it more concentrated, I'm just going to add less of the solvent. Okay. Now we're going to look at why things dissolve. So think about it. You know a lot about this already. Think about things that dissolve in water. Think about things that don't dissolve in water. All right. What is that related to? It's solubility. Solubility literally means like the ability for it to dissolve. So the ability for a solute to dissolve in a solvent. But there's a little note. It's got to be at a specific temperature and pressure, because if you change that, breaking the rules, okay? Things change. So if you say something is soluble, like salt is soluble in water, you mean that it dissolves. It has a high solubility. If you say that something is insoluble, that means it doesn't really dissolve and it has a low solubility. Okay, so like if you mix oil and water, it's a low solubility, so we say it's insoluble. The type of substance affects solubility. So here's where we're going to have to pull back from far away earlier in the year, some stuff from your brain, and you're going to have to remember it. So we're going to tie it in here. Okay, so you need to remember ionic, polar, and nonpolar. So what do I mean? Well, ionic may be the easiest to remember. We have a metal that ends up with a positive charge because it loses electrons. And then we have a non-metal with a negative charge because it gains electrons. And then that negative and that positive attract and make an ionic bond. Okay? And that positive cation and that negative anion, they hold charge. Okay, that's going to be relevant to what we need to remember. Okay, now, what if we have something that is covalent? Well, it could be either polar or nonpolar. So if it is polar, what happens is the electrons are pulled closer to one of the atoms because it has a high electronegativity. And so that end, because it pulls the electron closer, it is partially negative. That is this little symbol right here, partially. That is partially negative. And then the other end, on the flip side, is going to be partially positive because it's partially losing the electrons. So it's losing that tug of war, so it ends up with less of that electron charge, so it ends up partially positive. And then when we have something that is nonpolar, those electrons are just shared equally. So it's like no one's winning the tug of war. The little flag is just hanging down in the middle, so no charges. That is what is important to know, because that is what ties into solubility. How do we figure out if something is polar, nonpolar, or ionic based on its bond? Well, we subtract the electronegativity values. Really low, like under 0.4, 0.5, that's nonpolar. Big, like above like 1.7, that's ionic. And then in between, that's polar. Water is polar. Remember this, because literally this is why water is a universal solvent. It is a great thing to dissolve stuff in. So I like to think polar bears love polar water. Water is polar. All right, so there's this rule called like dissolves like. And it's a great rule, but not if it doesn't make sense. So I like to think about it like this. Solvents that have charges dissolve solutes with charges. And solvents without charges dissolve solutes without charges. Makes sense, yes? Okay, so what do I mean? Well, remember how polar has that partial positive and partial negative? Well, that's a charge. Remember how ionic has a positive and a negative? Well, that's a charge. And then remember how for nonpolar, either those electrons are shared equally, or in this case right here, so do you see this one? This is polar, but do you see how there's a pull from every single side. So if you have equal pull all the way around, it still ends up nonpolar. So it ends up with no overall charge as a molecule. How does that relate? Well, things that are polar, like if I have a polar solvent, is going to dissolve things with charges because polar has a charge. So it's going to dissolve anything that's polar or anything that's ionic. And if I have a nonpolar solvent, well, that doesn't have a charge. So it can only dissolve things that also don't have charges. So other nonpolar solutes. Okay, so this is why water and oil don't mix. Okay, because water is polar and oil is nonpolar. Okay, so substances with charges and substances without charges do not dissolve each other. They don't mix. So polar has charge. It cannot dissolve in something that is nonpolar. Now, how does this relate to our lives? Well, water-soluble vitamins like vitamin C, we get it from our diet. And the excess is eliminated from our kidneys because it's just filtered through. It's soluble in water. Fat-soluble vitamins like vitamin A also come from our diet, but it's fat soluble, so it doesn't get flushed out in your kidneys. So it can actually accumulate in your own body fat and it can become toxic. Temperature also affects solubility. So for solids, we increase the temperature, it increases the solubility. Okay, so we use hot water, we can add more salt to it, dissolves better. With gases, we have to decrease the temperature in order to increase the solubility. So if we have warm water or syrup flavored water for like soda, it is going to dissolve less carbon dioxide gas. Those bubbles in soda are from carbon dioxide. So if I were wanting to put a lot of bubbles, a lot of dissolved carbon dioxide into the soda, I would need to make sure I did it at a low temperature because that is going to hold more of the gas particles in solution. Now remember, pressure also affects gases. So if I squeeze it down, if I increase the pressure, I'm going to force more of those gas particles into the solution. So this should sound familiar because, look, when you open up a soda for the first time and you go here, psh, why? Well, because you just released the pressure. And now some of the gas is like, yes, and it escapes the solution. Okay, because that pressure was forcing those bubbles to be in the solution. So it's what happens right here. Psh, psh, psh. Or in this case, it's a little bit more problematic. Has that ever happened to you? So warm soda is going to taste flatter, less bubbly, because there's less of that carbon dioxide dissolved. It also won't hold the gas in solution as long, so it'll get flat faster. So first of all, there's less bubbles when you pour it, and then also gets flat faster. All right, in class we're going to practice with a blue bit, but you should know it.